The solar geometry studies the movement of planets around the Sun and is also used to calculate the apparent solar paths seen by an observer on Earth. Knowledge of solar geometry is important to understand the interactions between Sun and buildings. It allows to better control sunshine, daylighting and shading phenomena in architecture, in order to ensure optimal levels of comfort and energy efficiency. The Earth moves along an elliptical orbit around the Sun in a little more than 365 days and also rotates around its own axis, inclined by about 67 degrees with respect to the plane of the orbit, employing about 24 hours to perform a complete turn. The Earth's position during its own rotation may be defined by the hour angle omega, which is the angular distance between the meridian of the observer and the meridian whose plane contains the Sun. This angle varies 15 degrees per hour. It is 0 at noon and has positive values in the morning and negative in the afternoon. For example, at 10 am, omega is plus 30 degrees. At 1 pm, omega is minus 15 degrees. The tilt of Earth's axis respect to the plane of the orbit is constant, but the angle formed between the line joining the center of the Earth with the center of the Sun and the equatorial plane changes day by day, or better, instant by instant. This angle is called the solar declination delta, is equal to 0 at the spring and autumn equinoxes, is plus 23.45 degrees at the summer solstice and minus 23.45 degrees at the winter solstice. As a consequence of the Earth's movements around the Sun, an observer on the Earth perceives in the course of the year different solar paths, characterized by variable heights and lengths depending on time of year and latitude. Each point of solar paths corresponds to a specific position of the Sun in respect to the observer. This position can be defined through two angular coordinates: solar altitude beta, represented by the angle between the line joining the center of the Sun with the observation point and the horizontal plane; solar azimuth alpha, which is the angle measured on the horizontal plane from the south pointing coordinate axis to the projection of the same joining line. It has to be noticed that in some of the literature, instead of the angle beta, the zenith angle zeta z is used, which is the complementary of beta. Solar paths related to a particular latitude can be read easily on the so-called polar diagram. In polar diagrams, solar paths are represented through a stereographic projection onto a horizontal plane, on which the four cardinal axes are represented. The base of each polar diagram is represented by a series of concentric circles and radial lines. The values of solar altitude beta are represented by the circumferences. The outermost one corresponds to beta equal to 0 degrees, horizon, while the center corresponds to beta equal to 90 degrees, zenith. The values of solar azimuth alpha are indicated by the radial lines and can be read out as the angular distance from the south pointing coordinate axis, with positive values eastward and negative westward. For example, south corresponds to alpha equal to 0 degrees, east corresponds to alpha equal to 90 degrees, and northwest corresponds to alpha equal to minus 135 degrees. In the polar diagram is drawn the average path of the Sun in the solstice months, December and June, and 5 pairs of symmetrical months in which the plots are practically coincident: January and November, February and October, equinoxes of March and September, April and August, May and July. The slightly curved vertical lines intersecting the 7 monthly paths join the points corresponding to the same hour of the different months. Let's refer to an example to understand how polar diagrams work. We want to know what is the apparent position of the Sun in a place located at latitude 15 degrees north in the average day of February at 2 pm. Firstly, we identify the line corresponding to the month of February and the one corresponding to 2 pm. Then we find the point where the lines cross. The circle and the radius passing through that point respectively indicate the solar altitude and azimuth values. If they are not exactly matching the point, the value is obtained by approximation. The polar diagram can be used to study the position of the Sun in the different months of the year and at different hours, with respect to a building or to a group of buildings in order to understand which will be the most irradiated and which the shaded surfaces in the different periods. A specific diagram must be traced for each specific latitude because the apparent movement of the Sun changes with the observer's position on Earth. For example, here you can see the diagram related to the equator, to the latitude of plus 23.45 degrees north, Tropic of Cancer, and to the latitude of minus 23.45 degrees south, Tropic of Capricorn. In order to study the interaction between a given surface and the Sun, for example the incidence angle of the solar radiation striking a wall, it is useful to define the spatial position of the surface by using the following parameters. Gamma, surface azimuth, is the angle between the horizontal projection of the normal to the surface with the south pointing axis. It is 0 degrees when the orientation coincides exactly with the south and takes positive values eastward and negative westward, so that you have gamma equal to plus 90 degrees for east, gamma equal to minus 90 degrees for west, and gamma equal to 180 degrees for north orientation. Psi, tilt angle of the surface, indicates the angle formed by the surface with the horizontal plane. It is 0 degrees for horizontal and 90 degrees for vertical arrangement. Theta, incidence angle, it is formed by the sun rays with the normal to the irradiated surface. It is 0 degrees when sun rays are perpendicular to the surface and 90 degrees when they are parallel to it.